We have been discussing the UML meter model, and the UML meter model mainly discusses structural aspects in the sense that our main example was a class diagram, and then we have been working on questions how to represent the class diagram, the structural model, in terms of a meter model. It is also possible to handle behavioral dynamic meter models. They can be treated in meter models as well, and the example that I'm going to discuss here are state machines. I'm going to present a general three-level meter model for these state machines. I'm going to discuss the realization in use. And after we have seen some of the details of this three-level meter model, we will also see that in general meter models with more than three levels can be realized. So, three-level meter modeling of behavioral aspects. Three-level meter modeling, that means we have a model, we have a model instantiation, and we have a meter model, and between each two levels we have an instance of relationship. So the model is an instance of the meter model, and the model instantiation, as the name suggests, is an instance of the model. Let us start with a model, with the middle part here. So what we see here is a state machine, an automaton, in principle an automaton. It's a state machine that describes the process of paying a particular amount of cents, American cents, with coins. In the US, you have the coins nickel and the dime. The nickel is worth 5 cents, the dime is worth 10 cents. And what we see here, what is represented in this state machine is a process of the general process of paying 25 cents with nickel coins and with dime coins. And one option, and you see the states are named according to the sum that is already paid. So the states are called paid 0, paid 10, paid 20, paid 25, and there are two other states, paid 5 and paid 15. And one run through the state machine, you see it over here. So first a dime, then a dime, and then a nickel. So you have paid 25. Or you can go here through the other way. You can pay with choosing only nickels, only 5-cent coins, nickel, 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 and you end up in 25. Or you can have here an arbitrary mixture when you, for example, pay a nickel, pay a dime, and pay a dime again. And the options that are available here in this state machine are all options to pay 25 cents for coffee or for a drink or whatsoever. So this is a general model. Here on this level we have the model instantiation. A model instantiation is one particular run through this higher level model. taking the model and instantiate it, give the model instantiation, taking this model and using the model. First we pay a dime, then we pay a nickel, and then we pay a dime again. So this model here corresponds to a particular path through the state machine. So that's the model, and that's the model instantiation. On the next level, we have the meter model. So the meter model, the aim of the meter model is to have, in quotes, something. So when we instantiate the meter model, we can obtain this model here. And in the meter model, we have two classes. Namely, we have the class state, we have the class transition. The states correspond to the rounded boxes here. The transitions correspond to the arrows or to the edges in the graph. States correspond here to the nodes in the graph. Transitions correspond to the edges in the graph. A transition has exactly one source. A transition has exactly one target. So this is, for example, one particular transition which goes from page 0 to page 5. This transition, the source of this transition is the state page 0, and the target of this transition is the state page 5. So this arrow will become a transition object here, and there is a name associated with the transition object. The name will be nickel, and as you see here, there are various transitions with the name nickel, so the name here will not be unique. On the other hand, in this particular example, the names of the states will be unique when we build an instantiation. Next, we will see two realizations. So we see two use models now of this picture. In one use model, the upper part is the model and the lower part is the instantiation, and in the second use model, the middle part is the model and the lower part is the instantiation. So there are two views on this figure here, on this three-level meter modeling. That's a direct implementation of the, I've called it the nickel dime machine in use. The nickel dime machine has a class diagram. The class is called nickel dime machine, and it has two operations, namely nickel and dime. And this class is associated with a state machine. The nickel dime machine live, that's the name for the state machine, and that's a protocol state machine, and the protocol state machine now rules in which order these operations are accepted. And as well as you see here, this graph, this protocol state machine directly corresponds to the state machine in the previous model. So we have a state called page 0, state page 10, state page 20. We have a state page 25, which is a final state. We have an initial state, prenatal. We have two further states, page 5 and page 15. And the transitions here, first we have this create transition, which is not explicitly mentioned here, but we do not have initial states and final states here. Initial states and final states are sort of optional, can be regarded as optional, but in a use UML protocol state machine, you must have an initial state. You do not necessarily have to have a final state, but here I've decided to have one final state. And you see here the transitions are exactly the transitions that have been represented in the model before. We have a particular run that is represented in terms of a command list. So first we create an instance, an object of this class, new nickel dime machine, NDM, nickel dime machine, NDM, that's the identity of the object. And then we call 3 operations in a particular order on this NDM object, and that's exactly the same sequence of operations that we had before: dime, nickel, dime, dime, nickel, dime, all called on the NDM object, and this is on the one hand represented in the command list. This is on the other hand can be represented as an object diagram. So we have here this NDM object and the lifeline of this object. And as you see here, I'm not sure whether we have seen it at all. As you see here, I have taken the option to represent on the lifeline of an object the particular states. And here you nicely see that first the object is in state page 0, then the object is in state page 10, then the object is in page 15, and then the object is in state page 25. And this exactly, first we have the create, then we have the dime, then we have the nickel, and then we have the dime again, and this dime, nickel, dime again. These operation calls exactly correspond to one particular run through this nickel dime machine, and that's a representation of a model and an instantiation of the model. So this is the model, and this is both the command list and the sequence diagram represent an instantiation of the model. So roughly speaking, the 2 lower levels have been represented here in this use model. There is another way to represent this state machine, namely a way to consider now this as a model and to consider this as the instantiation. And the second way of representing we have a class diagram consisting exactly of the meta model class diagram that I've been presenting over here. So this is here we have a class diagram with the 2 states, with the 2 classes, state and transitions, and 2 associations for representing source and target of a transition. And in principle, again, this graph represents this model, but this time this graph is an object diagram, a model instantiation of this meta model. So the model is an instantiation of the meta model. And here you see now, well, you see we have different objects. We have the state objects as before. Page 0, page 10, page 20, page 25, page 15, no, page 5, page 15. And we have now, instead of having the arrows here, of having the edges, we have the transitions explicitly represented as objects. And I've taken a particular way of naming the transition objects. So, for example, the transition between page 0 and page 10, the transition is called T from 0 to 10, or say the transition from 15 to 20. That's a transition called T15 underscore 20. And well, in the transitions you have the name objects. Here you have all the first four are all nickel transitions, and here on the left hand side we have 1, 2 dime transitions and another nickel transition and another dime transition over there. So the name in the transition objects is not unique. As an additional option, what we have here, we now have this object diagram, and of course we can now state queries against this object diagram. So in a sense, the option to state queries here is the option to take this model here as a model instantiation and check particular properties with queries. So the query that I'm assessing over here, let's try to make it a bit larger. The query here is I am having a let transition here. The S is state all instances, so the S represents all state objects. And what I'm doing here is from the states, from all states, I'm selecting those states for which the following is true. I'm selecting those states as for which the following is true. I'm considering the set of states consisting only of the S, and then I'm checking which states are reachable through the transit S role from this state, and then I'm going to the transition, and then from the transition I'm going to the target. So I'm obtaining here an expression that goes from state to state again, or from a state to a set of states, and I'm building the closure of this expression. So I'm asking from which states is it true that I'm starting from the state, I'm building the closure of this expression, first going to the transition, then going to the state, and I want to reach the complete set of states again. And you see here, so the query asks the question, which are the states, starting from the states, I can reach all states with a closure operation. And you see here there is only one state that has this property, namely the starting state. And when I'm interested, when I would be interested in other properties, I could, for particular states here, I could check here different OCL expressions and obtain different results here. So the exploration is done, the exploration and the property finding is done in this example by formulating OCL expressions. And the OCL expression is about finding particular states or particular transitions. Okay, so these were two representations. So the first representation in use were the first two levels, where we had the representation of the state machine in form of a protocol state machine. And the second representation was a representation of the state machine in form of an object diagram, and the object diagram belonged to a meter model that represents states and transitions, and the meter model, with a meter model one can represent state machines. Okay. So this is a 3-level metamodeling. I mentioned in the intro before, metamodels with more than 3 levels are possible. So let's jump to something which is labeled here 5-level metamodeling. In the 5-level metamodeling example, we have the metamodel, the model, and the model instantiation. So this part here is, the middle part is as before. We have here a run through this state machine, and this is the metamodel in terms of UML representing the concrete state machine. We can do now the same. We can play the same game that we have been playing before. We can take this class diagram and ask, what is the metamodel for this class diagram? So when we consider this as a metamodel, then we are asking about the metamodel. And so when you look at this here from an abstract point of view, you say, well, we have classes here, namely we have the class state and transition. We have roles, source, transit, target, and target. These are the roles. And we have associations, namely we have 2 associations. So when I would represent this class diagram with this metamodel, I would obtain 2 class objects, 4 role objects, and 2 ASOC objects and the respective links here. So I can go 1 level higher to obtain a meta model. We can also go 1 level, we can also step 1 level into the lower direction. We have been talking here about dimes and nickels. In fact, dimes and nickels you can build specializations for dimes and nickels. When you look into the Wikipedia pages for American coins, you will, and in particular for nickel and dime, you will learn there is not the dime as such, but there are, so to speak, various versions or variants of the dime which came out or which were published, which came into use in probably in different years, and these are called the Roosevelt dime, the Mercury dime, and the Barber dime. And so when we want to, instead of considering the model instantiation, when we want to reflect these specialization, then we can build a model instantiation, which follows the model instantiation. So instead of saying here, well, we take a dime and we go from page 0 to page 10, and then we take a nickel to go from page 10 to page 15. We say here something more special on the next lower level of the metamodel stack, and we say, well, we do not have a general dime, but we take the Roosevelt dime to take this transition, and the Jefferson nickel will. These were the Roosevelt, the 3 different kinds of dimes, and here there are also 3 different kinds of nickels: the Jefferson nickel, the Buffalo nickel, and the Liberty Head nickel. Yeah, instead of taking here the general nickel, we take here the more particular nickel, the Jefferson nickel. We take the transition over here. So the transitions are made more special, and we could also make the states more special. As you see here, I have called the states in a different way. I've used a different notation, and this is to reflect the order and the order in which the coins were inserted into the machine. So, for example, this state is called paid 10, the 10 first, and then the 5 comes as a second coin. So this state here, this state 10, 5 corresponds to exactly this path here. So this state machine will distinguish between this path, where first the dime comes and then the nickel. That will be a different state from the path where first the nickel comes and then the dime comes. So in this state machine, in the state machine below here, I will have the states paid 10, 5, and I will have the state paid 5, 10, which would correspond to, both would correspond to these two different edges. So, and this example in sum, this example shows that when you have this 3-level modeling, you can extend your meter model by going into the upper direction, and you can extend your meter model by going into the lower direction. By going into the upper direction, your meter model becomes more abstract, and by going into the lower direction, your meter model becomes more special. So this is just an example that one does not have to stick to the 4-level meter modeling philosophy of the OMG. One can have typically a 3-level style of meter modeling, but it is also possible to say, to have something what is shown here, a 5-level meter modeling architecture. So in principle, you can go an arbitrary number of levels into the upper direction and an arbitrary number of levels into the lower direction until you reach atoms here, until you reach photons or whatever you want to do in physics over there. So what is following here? There are some slides, which additional slides which handle, which take the view that meter models, and in particular class diagrams together with constraints, can take a similar role that grammars take in traditional software development, but I will not go into the details here. We have learned a lot of things about meter modeling, and we, for at least for this teaching unit, we stop here, and I thank for your attention.